Hi class, in this video I'll be walking you through how to carry out analyses related to spatio-temporal autocorrelation in R. First, we'll go over a method to check for temporal autocorrelation in your data using the ACF or autocorrelation function plot. We briefly covered this in presentation 1, but we're going to look at it again in greater detail and build up from there. Then we'll do a quick review of how to detect spatial autocorrelation in your data using a variogram. Finally, we're going to combine spatial and temporal analysis together to create variograms that incorporate both of these dimensions. We'll be creating 2D and 3D variogram plots. First things first, install the package Spacetime if you haven't already. Spacetime contains functions that help analyze spatio-temporal data and was created by Edzer Pibesma and others over a decade ago. After you've installed Spacetime, we'll activate all of the packages that are needed to run today's code. They include gstat and lattice. In this video, we'll be using the air data that comes with the Spacetime package. This dataset contains daily averages of air quality data, more specifically concentrations of PM10, measured by various stations distributed throughout Germany between 1998 and 2009. Let's go ahead and load in the air data and see a list of what it contains. So we've got air quality data locked up in the air data set, and the dates on which the data were collected stored in the dates data set. Now, to see if the air data has temporal autocorrelation, we can create an ACF plot, which we've encountered several times in class to check for spatial correlation. In order to create an ACF plot, though, there can be no missing values in our data set. So we're going to just look at a subset of this data to make the analysis more manageable, specifically just the data collected between 2005 and 2010, and remove the stations with missing data. Okay, out of this subset, we'll go ahead and arbitrarily pick the first station to test temporal autocorrelation with. So the first station out of this subset is 001. So we'll go ahead and now apply the ACF function to plot for temporal autocorrelation. The plot we've generated here shows ACF values on the y-axis and a lag on the x-axis here. The lags represent days in this case, so we are looking at temporal autocorrelation over a period of 30 days. By definition, it will be 1 at lag 0, which we see here. It decreases effectively to 0 after about 10 days, and even after 1 day, the autocorrelation is only about 0.5. This shows that air pollution at this station is not all that persistent. Now we'll go ahead and turn our attention to determining spatial autocorrelation using a variogram, which should be a bit of review. So to begin, we're going to create a time-averaged variogram by first sampling 100 time instances randomly. Then we're going to select these instances as a spatial points data frame, add a time index to them, then bind them together in a single spatial points data frame with the time index ti. Okay, once we've done that, we can create our pooled variogram and plot it. We see that the variogram here doesn't fit the data all that well, but it is evident that we've got some spatial autocorrelation here. To get a more exact idea of the correlation, we can enter code to see the still in range. And we see that right down here. And we see that up to a distance of about 53 kilometers, we've got spatial autocorrelation in the air data. Now let's go ahead and dive into making variograms that take both the spatial and temporal dimensions into account. We can start by fitting a spatio-temporal variogram the usual way. We can generate two types of variograms here. And let me go ahead and plot the first one, which is called a variogram map. And this might take a minute. And okay, so this is a variogram map, and this is what it looks like here. And we're going to go ahead and plot a second sort of variogram, which won't take as long to load. And these are parallel variograms. I prefer this graphic as I think it's easier to interpret. Here we see that the average spatial dependence at lag 0 is well structured with a low nugget and increasing to about 60. As the time lags increase, the total still increases, but the partial still, which is equal to the total still minus the nugget, is actually decreasing. This signifies less spatial structure with increasing time. By 10 days, there's virtually no spatial structure. And it's also interesting to note that at all lags after the first, there's better correlation at about 20 kilometers shown by these dips here than at 0 kilometers. We can try to model the spatial temporal dependence shown in this variogram using two methods, the metric and separable models. Metric is the simpler of the two, and it involves rescaling the time dimension to match the spatial dimension. Let's run the code and plot the metric model. Okay, we should now be asking ourselves how well this fits the empirical variogram we just looked at. Well, we see that it fits the original variogram well at lag 0, but not that great for longer time lags. Based on these results, we can say that time and space don't have the same structure and that another model might be a better fit. So let's go ahead and try the separable model, which fits time and space independently, so it allows the dimensions to retain their units. Okay. So now after plotting this model, we see that the fit to the empirical variogram is visually better than for the metric model. We see the spatial structure for lags up to about 5 days with the increasing nugget similar to the empirical variogram. Now to mathematically determine whether the metric or separable model is better, we can go ahead and calculate the mean absolute errors, MES, with these simple lines of code. Because the MSE value is smaller for the separable model, shown here, we can say that the model is indeed the best fit for our air quality data over the metric model. We can also plot the variogram maps in 3D by creating a wireframe and compare them by incorporating each variogram map as a panel in a single plot. I think it's a neat way to display your spatial data. and I encourage you to play around with this code. This concludes the R walkthrough on spatio-temporal autocorrelation, and if you have any questions, please post them on this week's discussion board. Thank you.